All right. Hello, hello. It's astronomy time again here at UACNJ, United Astronomy Clubs of New Jersey. So we are live here on site while people are filing down for our actual live audience. A couple things. We are here live. We do have in-person presentations. Unfortunately, with COVID still active, it is through reservation system only. So if you go onto our website, uacnj.org, you can find a link to the Eventbrite reservation system, and you can get a ticket, which is completely free, to come up and enjoy our presentations. On our website, you will also find a list of presentations we have coming up in the next weeks. We are open every Saturday, April through October, and we will be doing live on-site presentations as long as weather permits, since we do have them outside now with the COVID restrictions. So, tonight's presentation is Anatomy of a Star with our very own president, Paul Fisher. Paul, helps if I have it on the right side of the page. Paul Fisher has what is BE?
Bachelor of Engineering. Stevens is one of the only schools that gives a Bachelor of Engineering.
I learn something new every day. He has a Bachelor of Engineering in Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in celestial objects, Paul's official start in amateur astronomy was one night 8 years ago, lying in an awkward position on his roof in the freezing cold, holding a pair of binoculars. He caught a brief, clear glimpse of the Galilean moons of Jupiter and was hooked. After some introductory reading, he purchased his first telescope and is now an active member of Northwest Jersey Amateur Astronomers and an observer and now our president at United Astronomy Clubs of New Jersey. And you see, he still manages to frequently find himself outside at night in awkward positions in the freezing cold, still seeing neat stuff in the night sky. And with that, Paul Fisher.
Hello, everyone. Thank you for the welcome. And thank you, Kim. Tonight, I'm going to present to you the anatomy of a star. And as Kim mentioned, I am a member of NWJAA and observer up here at UACNJ. Okay, so let's get right into it. I'm an amateur astronomer, and I want to go into a couple of things about what I'm going to present to you tonight. First, I mentioned amateur astronomer because these people right here, these guys are the professionals and I'm the amateur. So for any correct information, I refer you to these gentlemen. Kenneth Lang. This is the specific book I read, The Life and Death of Stars. You can find it here from this publisher here, Cambridge University Press. And then Alex Filipenko, he's a PhD, so Dr. Filipenko, and he's it's a great course, a video series, Understanding the Universe, an Introduction to Astronomy. So I pulled heavily from those two gentlemen. Like I said, any mistakes that you see in the presentation, I'll take that blame. These guys are the experts. All right, so what are we going to cover tonight? First, we're going to introduce you to a particular star, and it isn't quite that simple, so we'll explain a little bit about that particular star. And then we'll give you the inside scoop, in other words, what's going on inside a star. Everyone loves an origin story. If you watch any Marvel movies or anything like that, origin stories are always cool. We'll talk about how stars are born. What makes a star tick? What's the engine that drives it? How does our chosen star compare to other stars? And there's a lot of other stars. And then what happens at the end of the story, at the end of the star's life? Introducing the sun, sort of. Now that you come out to an astronomy site and maybe you want to see something a little bit more exotic than the sun, well, that's where the sort of comes in, because let's do a baseline understanding of stars and how we know things about the universe. First of all, let's clear up one thing. Yes, we do get this asked. It seems basic, but people do ask. Yes, our sun is a star, and other stars could be considered suns of their own planetary systems. However, we must be of two minds on this particular subject. First, when compared with data and measurements from other stars, the sun is really kind of, well, an average and unremarkable star. However, on the other side, we are very emotionally, historically, geologically, and evolutionary and physically attached to our own star. It is indispensable to us. So the sun is very special to us, but in the grand universe, it is a very average star. We wouldn't be here without our sun. To us, it is the most important star in the universe. All right, so I gave that little caveat on that other slide. Our model star is the sun, sort of. Why sort of? And here's a tongue twister. Astronomers are actually actuaries. What does that mean? The sun has been around for 4.6 billion years. The entirety of the human race has been around for about 200,000. So how many people have seen the birth of the sun? None. Correct. And how many people here will see the death of the sun? None. No, you. Good luck trying, but I'm going to bet against you. So correct. We don't see the entire life of a star. It's impossible. When looking at stars, astronomers not only have to take into account the speed of light and the expansion of the universe, but also their statistical variation. So statistically, they see suns or various sun-like objects, stars, in various points in their life. So we know about our sun's origin by looking at the birth of a star that's away from us. We also know what the probable death of our sun is going to be, based on what's happening out in the rest of the universe. So when we have to take into account and do all those funky maths for the speed of light and the expansion of the universe and all those complicated things, it's not a bug, it's not extra difficult, it's actually a feature. It allows us to know more about our own sun. And knowing our sun, and here it says it works both ways, being next to our sun and being able to bring satellites out to the sun and take measurements and all that type of stuff, it works in the other direction. We can take that information and apply it to our knowledge of other stars. So it's compatible, and it's actually a feature, not a bug, once you work through all the complicated math and all that. Our particular star is actually a very sun-like model then. So it's a combination of our knowledge of our observation of the stars and our observation of the sun. It's a model. It doesn't actually exist. It's something that we cobbled together to understand the whole. It's maybe not a stretch to consider it an every star. So let's get into our model of the sun a little bit. So far there's been a lot of text up there and not a lot of very interesting pictures. So let's start with one picture here. The Solar and Heliospheric Observatory, Soho, You can find it at Soho, www.nascom.nasa.gov. The picture I'm about to show you was about a half a year ago it was current, and I did that for a reason. I'll let you know in a minute. And this is called the HMI. It's what you see with a standard solar filter, a white filter, a beta filter, all kind of the same thing. It was this image is what you would see. And the reason, let's see, I said, the reason I gave you this information here, you can't search on Soho and get this particular mission from NASA because you'll get that area of New York City instead, right? So what you need to do is take NASA as one of your keywords and Soho as your other keyword and type that into Google, and then you'll get this mission. And you can see these images, or this particular image, but there's other images also. So here's an image of the sun. You can see why it's called a white filter, because the sun looks white when you look through a beta filter. And you can see here the sunspots on the sun. There's one here with a label on it, and one here with a label on it. It also gives you just from a size representation point what Jupiter looks like next to compared to the sun, and what the Earth looks like compared to the sun. All right, so that's one place where you can immediately understand a little bit more of the sun. In fact, this is updated live every day. I forget the refresh rate, but it's refreshed frequently, so you can basically get a live picture of what the sun looks like. I also have a filter for my telescope. I can get something that's not anywhere near this resolution, but I can get a similar picture in my telescope. So that's our first picture. Let's talk a little bit more about what's inside the sun. The materials of construction of the sun, first of all, we need to know astronomers are a little weird. They think that there are 3 things in the universe. Well, they know that there's more, but they'll classify things as hydrogen, helium, and metals. Forget that periodic chart. It's hydrogen, helium, and metals. The reason for that is because, by and large, the Big Bang created mostly hydrogen and helium, and the other elements in the universe are relatively scarce compared to those 2 elements. That's what it says. They are by far the most abundant elements in the universe, and you can see here with our sun model, that hydrogen is mostly one of its major constituents. It's 71.54%. Helium's at 27.03%, and metals, which, if you remember, is everything else, is 1.43%. All right, and I'm going to, let's see if I can do this properly here. This is a spectrum. So metals isn't really satisfying to us, right? Because we know that the universe is made up a lot more than just helium and hydrogen and helium. And here we can see what's called a spectrum. So from our sun's light, let me use this because that's just easier. We can see along here that various elements in the spectrum, so this is just Roy G. Biv, the rainbow. That's the various frequencies of light, and we're going off a little bit into the ultraviolet and infrared here. That these lines are absorption points where the light is hitting a element, and it is exciting an electron, and when it excites that electron, that light is absorbed. So we're getting nice big, I'm being attacked by our presentation here. So this light's coming through from the sun, and then these are getting absorbed by the material in the atmosphere of the sun, the various elements. Because what's happening is that light comes and hits that element that's floating around in the atmosphere of the sun, and elsewhere in the sun, but we can see it through the atmosphere with the spectrum. And then the light's coming towards us, it hits that element, and then it gets scattered in a different direction as it's released. And that's what causes the shadow. It's not like that sun, that shadow is just forever stopped from reaching anywhere, and it would just an accumulation of light. It just gets scattered in a different direction when that energy is released. So that's the spectrum, and that's what's happening there. Let's see if I can go over here now. And we talked about the various elements, and I know you can't read this chart very well, but over here is hydrogen and helium. Over here is lithium, beryllium, and boron, and you can see an interesting dip right there. And then you can see the rest of the elements. Now let's talk a little bit about what's going on there. This is chart is logarithmic. This is 10 to the 12th up here, and this is 10 to the 2nd down here. So it's not that there's 10 times more stuff up here, it's 10 zeros worth of times more stuff up here. Okay? So hydrogen and helium, really a lot of that stuff, really a lot less of this stuff. And this stuff, there's an interesting dip. The reason is, this is Big Bang up here. This is stuff created in stars and has to do with stellar synthesis of elements. And this is a different mechanism. And we won't get into what it's called, but the mechanism is that this stuff is actually not created in stars, but is created by cosmic radiation. So there's a completely different mechanism for this stuff, which is why it's so rare. we had a ghost in the machine there. All right, so let's play a game here. This game is what physicists use when they're grappling with different difficult concepts. They try to think of things that are in our everyday or within our ability to estimate, and compare it to things that are of astronomical size, very difficult concepts, very long distances. And when I say very long, mind-blowing, which is why they have to bring it back and compare it to things that they do comprehend easily because it's of everyday experience. So here's the core temperature of the sun. It's at 1.56 times 10 to the 7 kelvins. What's the when it's 0 degrees, that's 32 degrees Fahrenheit. When it's 0 degrees, how many Kelvin is that? 273 versus 1.5, so versus 1 with 7 zeros, all right? So that's the difference in the temperature. So that you get the appreciation when you compare. The core pressure, how many atmospheres are here right now?
At least
one. Around 1. In the center of the sun, 1.97 times 10 to the 11th. Almost 2 with 11 zeros following. The mass of the sun, 1.9 times 10 to the 30. I know what I am about. I'm not going to, internally, just take your weight and compare. All right, the diameter of the sun is 1.4 almost million kilometers. The distance to the sun is 1.5 times 10 to the 8th kilometers. The distance is 1 astronomical unit. When you see 1 like that as a pure number, you can be pretty assured that that means that this is the definition. The distance between the sun and the earth is the definition of an astronomical unit. And then distance in light years is 1 point, what's that? 4 zeros, 0.000016 light years. And what is that all in miles, which is very familiar to us? About 93 million miles to the sun. That's a lot. Okay, let's talk about that a little bit. Everyone knows about, everyone here has been in front of a campfire? Yeah. And you know that spot, right, where you're sitting just right in the, let's call it the butter zone, where you're getting, it's nice and comfortable in front of that campfire, and you move back a few feet, and you can't feel it anymore, right? You're cold. What is that? 10 feet? 15 feet? It depends upon how big the fire is. That's true. Well, this fire is 93 million miles away, and you can turn your face to it, and you can feel it. So that's how powerful the sun is. That's its energy output. 93 million miles away, you can feel it. That's that energy right there. 3.8 times 10 to the 26th. 26 zeros past that one. That's a lot of energy. And to jump 93 million miles of space, it's got to be, right? So what is the sun really? Inside, it is an incredibly hot, incredibly massive, and it's under gargantuan pressures. Those numbers are not off the chart because we just charted them, but they're ridiculous, right? Very hard to actually understand those numbers. It's not made up of matter as we normally experience. Those conditions are so extreme, it's actually a fourth state of matter called plasma that comprise the sun. Mostly the plasma is made up of hydrogen nuclei, which are protons. If you remember, there's one proton in a hydrogen atom. Helium nuclei, which we call alpha particles, just because of how they were named when we first discovered them. And then free electrons. And that is just a huge soup of those guys randomly going around. They are not associated with each other. There is no electrons so they aren't making atoms. It's this plasma stuff that's happening. The plasma is a fluid, even if it's extremely dense at the core of the sun. How dense? The average density at the center of at the core of the sun is 1.41 grams per centimeter cubed, and that is about 10 times the density. Oh, I'm sorry, I got that wrong. Let me read that correctly. The average density is 1.41 grams per centimeter cubed, and at the core, it is greater than 10 times the density of lead, but it's still a fluid. Everyone remembers what a fluid is, right? A liquid and a gas are both fluids. At least that's the technical definition. It just means not solid. Here's the solar structure, and we'll talk about the inside and the outside here because I can't get them both on the magnifier here. Let's talk about the inside here. Here you have, in our sun, the core, which was where the fusion happens. This radiative zone, which it's radiative because it's not moving around like a boiling liquid would move around. It's actually pretty still. And so the heat travels out by radiating through that stuff, and that stuff itself isn't moving around anywhere near as much as this zone here, which is the convective zone, which you could think of sort of like boiling. So that stuff, this material in the sun is moving up and down like you would in a boiling pot. So those three zones happen in stars that are the size of our sun, a little bit bigger than our sun, and smaller. It's a different ball game for suns that are much larger than our sun. And I'll go into why that happens in a minute. All right, so let's talk about the outside structure of the sun here. All right, so here we have the, I cut this off unfortunately. This is the photosphere, or the visible surface of the sun. This is the corona, which everyone remembers. You can see when the sun is completely eclipsed by our moon. And this is the chromosphere, which is, that's where the spectra that we talked about a little bit earlier comes from. That's the atmosphere of the sun. This is a coronal hole right here, where similar to a ozone hole in concept anyway. There's a flare here and sunspots over here. So that's the surface of the sun. And the chromosphere, the corona is actually the beginning of our sun's extended influence over the entire solar system, going through the solar wind and all the way out to the heliopause. All right, next slide. Also, another feature of our sun is that the sun is a magnetic dynamo. Is everyone familiar with what Jupiter looks like? Jupiter has bands on it, right? That's typical of any planetoid or object that's made mostly of fluid, of a gas in the case of Jupiter, of ice in the case of the ice giants, and in the case of stars made of plasma. They're all fluids. So what happens is that at the equator here, moving in this direction across any of these diagrams, the gas is rotating at one speed at the equator and a slower speed, most likely, up here at the poles. So what has happened? All these charged particles, the plasma in the sun, positive and negative charge, are moving at different rates. So if you take a positive charge and a negative charge and you move them by each other, that sounds a lot like magnetism and currents, doesn't it? And so if you move them at different rates, you start generating these huge magnetic fields, and these huge magnetic fields start twisting and turning. So here they are relatively straight at solar minimum. Here they are over time, they're starting to twist and turn. And here they are at solar maximum, where they're very chaotic. They're really bent around the sun. You can see that they start here at the equator, they start wrapping around the sun, and then they start looping and connecting. And that's what causes all the sunspot and CME and other discharges from the sun during any time, really, but especially during solar maximum. The solar cycle is 11 years long, from solar minimum to maximum and then back again. So that's what, remember, you have to come all the way back to the beginning in order for it to be a full cycle. It was originally discovered by recording the frequency of sunspot activity. Flares, sunspots, and CMEs, coronal holes, and other solar surface and atmospheric phenomenon all vary with the solar cycle. So maximum is what it is. More activity during maximum, less activity during minimum. It's important to study and predict solar events like the space weather and the space weather. That's all the activity that we just talked about. To protect infrastructure, satellites, and astronauts. Again, because the sun influence extends all the way from the surface of the sun all the way out throughout the entire solar system, and we feel that here on the planet, especially in our sensitive electronics and electric systems. All right, so a star is born. How cute, right? Because we're talking about baby stars. Oh, be very quiet, right? We don't want to wake any of the babies. Here's a stellar nursery. Here's two more. You can see some of the characteristics here, right? You can see that these stars are hidden by dust, right? They're kind of fuzzy and stuff. The stars are so bright, right? Here and here and here. There's a lot of light coming out from them. newly born stars. These are actually protoplanetary disks. All right, these are solar systems that are forming. So inside here, you know, this big blob here, that's not actually the star that's forming. It's actually smaller inside there. But these relatively empty spaces, guess what's forming in those empty spaces? Planets. Okay, the planets are starting to clear their orbits of material. So what is exactly a stellar nursery? What are the conditions for the birth of a star? Cold, dense, massive nebula, clouds of molecular hydrogen. They're really cold, they're really massive, and they're dense for space, not really dense as far as we're concerned. Cold means about 10 degrees above absolute zero. Massive means tens of light years across. They are protective of disruptive cosmic radiation. That's why they need to be so massive and so dense and so cold. The reason is that if you disrupt or move, what is movement also? What property does movement also give material? Heat. So if you're not cold enough, if you start moving material around, you start raising the temperature of the average material. And then, so you're no longer cold enough to start what is called, to reach the gene's mass and have that star-forming region start collapsing to spontaneously form a star. And what's actually causing that collapse? We're experiencing it right now because we're not floating. Gravity, right? So you reach this gene's mass here, and so that's a density needed. And the star, if it's quiescent, if it's calm enough, the material will start collapsing from its own gravity and start forming a star. However, that's not really necessarily 100% practical, because how often does it actually reach that gene's mass? I don't know that answer. Probably a professional astronomer knows that answer better than I do. But it's probably more likely that the collapse is assisted by perturbations from external events, such as a passing star, nearby energetic event, a nova or a supernova, or a combination, gravity waves, whatever, some sort of perturbation. Cloud collisions can even cause it. So the collapse can be assisted by an external event. When any of those things happen, you reach the gene's mass, or this external assist happens, a protostar begins to form. What is a protostar? So a protostar is not a star yet. It's a star heated by gravity collapse, but it hasn't started nuclear fusion yet. So no fusion yet, so it's not really a star. But what's going on? What's causing the heat? Remember the conservation of energy. It's a law, all right? And it applies to everything. And remember all that stuff you may have learned in high school, potential energy, kinetic energy, those things. The potential energy from the collapse, okay, as things move towards a gravitational center, right? Potential energy gets converted to kinetic energy. And I just told you that velocity, things moving, kinetic energy, is actually another way of describing heat. Enthalpy, which is heat energy plus pressure energy, will increase because we are increasing the kinetic energy, because things are falling towards the gravitational center. The gas is falling to the gravitational center. If the protostar is massive enough, eventually hydrogen fusion or burning can be sustained. So once that kinetic energy builds up, and once that density builds up, and all that material starts getting closer and closer, and it's more squished and more dense, fusion starts. Once fusion starts, the collapse is halted, hydrostatic equilibrium is reached, and we'll go into what that is in a moment, and voila, a new star is born. So you actually have a new star at that point. And here's hydrostatic equilibrium. You have to remember a couple things there to understand it. Plasma pressure pushes out. Okay, gravity pushes in. So the fusion, the heat and enthalpy and movement, the kinetic energy of the plasma is pushing the star out. The gravity is pulling everything in. But why is it stable? Well, you know, if you have two gigantic forces pushing back and forth, it doesn't necessarily mean one has to win, does it? In the case of the stars, obviously, since they exist for more than a millisecond, there is some sort of equilibrium. They come to some sort of agreement. A collapsing, remember, why is this then therefore stable? Remember, a collapsing fluid heats and an expanding fluid cools. So that's your stabilization mechanism. Changes in the rate of fusion are opposed by changes in the plasma expansion. So you start expanding, the fluid starts cooling. Once the fusion rate drops off, and then the star will have a tendency to collapse again. If the star collapses a little bit, the density starts increasing, the heat starts increasing, the fusion starts increasing, and it pushes the star back out again. So that it has that mechanism built in so that it's stable. And that's obviously very important when you are trying to wrangle two titanic forces. And let me see if I can zoom in here. It's just showing you here the core, the tendency for the gravity to push in, and the tendency for the fusion to push out, and those forces are in balance in a star. All right, so let's get into the fusion point, and this is, to me at least, very interesting. What's going on there? Sometimes what's going on makes a whole heck of a lot of sense. What's driving the fusion? Remember, that's the stuff that's inside the core of the sun. We talked a lot about it. It's very extreme stuff. It's moving very fast because it's very hot. It's under a lot of pressure. And remember, it's a fluid, so it can move around a lot. All the material in there is vibrating like mad, moving around in various directions, and the material follows this curve. In other words, the velocity of the stuff, the average velocity of the stuff is in here, along this axis, and the number of particles that are achieving that velocity are here, the tendency for the material to reach a certain velocity or the certain kinetic energy. Now this would be a bell curve, except in our case, zero is it's bound at zero. So this is a typical curve, a distribution curve, when one end is bound, right? Because you can't move slower than zero. That's why that's this shape. So what happens is that in order for for two hydrogen atoms to fuse, you have to reach a certain threshold value, this activation energy here. This blue area, this is, I'm reading this directly, shows the proportion of particles that have enough energy to make the reaction happen. So anything on this side is energetic enough to fuse. hydrogen into helium. But sometimes it's a head scratcher because it's a little weird up in the sun. The electrostatic repulsion. So remember, we're talking about protons. Protons are both charged positively. The electrostatic repulsion of the like-charged particles, the protons, actually dictate a much higher thermal energy for a particle collision to result in fusion. They've measured this stuff. So this activation energy in our sun is here. But they've calculated it that it should be really over here and that fusion shouldn't be happening in our sun. At least to the extent that it is. Why is it happening? Remember that very small things like protons, any particle, and when we are talking about particles in the sense of particle physics, any particle acts quite weirdly. Particle physics is really weird. And remember that they can behave like waves. Small particles can change position without actually moving through space. Some might call it, and you have to be very careful because it isn't either of these things, okay? But you can start to understand it by using the word teleport. So it actually will teleport from here to here without actually traveling through the space like I just did. And particles actually don't teleport like they're bamfing through space like a wizard. They actually, it's just, there's this uncertainty to being. In other words, your position doesn't actually really have a static place when you're that small. You more have a probability of where you exist. It's a wave. It's a wave function. So what happens is those small particles can change position without moving through space. They, quote unquote, teleport to the new nucleus. So that's giving an assist to the velocity of the particle. That teleportation happens, and that's why the activation energy is actually lower than if it actually just had to be velocity, kinetic energy. The higher a kinetic energy particle is, though, the faster it's moving, in other words, the more likely it is to tunnel, and that quantum tunneling is what it's called, is required to make fusion go. So that's a head scratcher a little bit, but that's what's happening in the sun. Let's talk about conversion. So what is that fusion doing for us? It's not actually burning. Fusion is not burning. You have to remember good old Einstein and his good old equation, E equals mc squared. And here's a couple of facts. There's about 700 million metric tons of hydrogen is converted to helium per second by the sun. In that same second, 5 million metric tons of that 700 million metric tons actually don't make it from hydrogen to helium. It is converted, that 5 million metric tons is converted to energy. So that's what's fueling the sun. And remember, the sun is, so if you see these huge numbers and you're like, 700 million, why is the sun still there? Well, remember, the sun is almost 2 times 10 to the 27th. So as many zeros as there are here, there's a lot more zeros here. There's 27 here, and only 1, 2, 3, 4, 5, 6, 7, 8 zeros. A lot more zeros on the actual weight of the sun. So don't worry, there's enough material in the sun there to go on for another 7 billion years. We're not about to run out. And just a matter here. So this is not actually, let's talk a little bit about the nature of matter and energy. One could think of matter and could think of this as an equivalency. So put that third line in there. Energy is matter times the speed of light. It isn't just a calculation. It's actually telling you a fundamental truth. Matter is actually kind of sort of It's just energy with a certain property associated with it that makes it look like matter to us, makes it look solid or liquid or whatever to us. Matter is actually a form of energy. All right, so let's go into sure.
Why is there actually enough material?
Hun, let me get the mic so people at home can hear the question, okay?
Why is there enough material to go on for another 7 billion years, but school claims that there's only enough for 5 billion years?
Well, different people have different estimates. I took my estimate from the books that I read. So they might have a different source of information. There's also, you got to think that there's different endpoints that one could use in their definition of when the sun ends. So the sun, someone could say that the sun is ending when it's no longer a yellow main sequence star. And some people could say it's not it's at the end of its life after its red giant phase. And those two facts that's 5 billion and 7 billion, could actually, you're really talking about the same thing. You just have different definitions of what the end point is. Does that answer your question?
Yes.
I think that's probably likely the explanation. But not knowing what your textbook says, I can't answer 100% with certainty. All right, so let's talk about why those, when we talked about the structure of the sun, why some suns have one structure and other stars or suns have another structure. Our sun goes through this fusion reaction. It takes 4 hydrogen atoms and it converts it to 1 helium atom or proton, 4 hydrogen protons to 1 helium proton, plus some light in the gamma range, in the gamma radiation range, and neutrinos. So this is the overall reaction, and this is the mechanism. So what happens is first 2 hydrogen protons collide. They form this intermediary, which is 2 hydrogen protons together, plus a positron and plus a neutrino. Then 2 of these things find each other, collide, and go into a isotope of helium nucleus, and then give off some gamma radiation. And then 2 of these guys find each other, form a full helium full helium nucleus, which is called an alpha particle, and then 1 hydrogen proton. So that is, when you add those together and cancel the intermediates out, they come back to this proton-proton chain. And that's the fusion reaction. That's the hydrogen getting converted to the helium in the sun, plus the very important neutrino and the very important gamma radiation you can see given off that's what's the power coming out of the nuclear reaction. Now, different suns have a different structure, and since it's not our model, I'll just tell you the existence of this CNO cycle, but I won't get into it too far. Larger suns have a more complex. It still has the same overall reaction, really. So hydrogen's getting converted to helium, 4 hydrogen to 1 helium plus gamma radiation and neutrinos. But it goes through this more complicated mechanism. And what happens is this stuff flies around at a lot faster rate. So that quiescent zone, that radiative zone in larger stars goes away. All right, let's compare our sun to other stars. And just let me see how much time I'm taking up, and I'm on time there. So what we can't, what do we know about stars? What we can't know from our observations sitting here on Earth. We can't know the size of stars or their luminosity from knowing their brightness. Light's brightness depends upon its distance from us. So we have to know already a star's distance what its brightness is, what its luminosity is. We can't know that because we don't necessarily know its distance from us. Light and distance has an inverse square relationship. Stars' brightnesses are classified by a measurement called magnitude, and stars' luminosities are classified, that's their innate brightness, how much light they're giving off in total. Can be classified by a unit of power like watts or absolute magnitude. So absolute magnitude, it sounds like a lot like this magnitude here, right? It's actually standardized, so they're cheating a little bit. They're using this nice magnitude that all the ancient astronomers were familiar with, measuring the brightness of stars, or the apparent brightness of stars, and they fixed a length away from fictional length from every star at 10 parsecs. So that's the light given at 10 parsecs. So that actually translates to a luminosity as a magnitude, because it would be as if we were looking at the brightness and every star was equally distant from us, which is not the case, right? So it's manufactured, and it can actually be a measurement of luminosity. What we can know from the observing light from the stars sitting here, or standing or sitting here on Earth. Black bodies, stars are approximately black bodies, irradiate with color intensities with a predictable curve. Knowing the curve shape, the color index of a star, we can predict the surface temperature of a star. And we'll go into that in a second. Knowing the surface temperature, the spectral type, and luminosity class, and a whole lot of physics, we can actually know the mass of the star, because the mass is driving the temperature, which is driving the surface temperature, which is driving the how much light the star is giving off. So knowing the star's mass lets us know many things about a star. And once we know the luminosity from all this physics and knowledge, and we know its brightness, and we know that there's an inverse square relationship, what do we finally know about the star? We know how far away it is from us, right? Because we know that inverse square relationship exists. We know how bright it is in our sky, and we know its luminosity from this physics. So now we know how far the star is away from us. So remember this. This is actually, we said this is through this region, the visible light, the stars giving off. Well, we take that spectra, and we do a plot like this, and for each of the colors, each of those light frequencies, and we get these plots, where this is how much light is coming off for these wavelengths of light. And then we finally come here. These are all the visual. We drew, the person who made this drew a rainbow in the visual spectrum of light. And and this is light coming off at these wavelengths. So knowing we know that's these curves I just talked about of how much light is coming off at different wavelengths, and different stars, different black bodies have different temperatures at which this happens at. And if you notice right here is this value of 6,000 Kelvin. And this 6,000 Kelvin has this peak of light energy coming off this particular black body at 6,000 Kelvin. That peak is right almost dead center in the visible range, isn't it? Well, keep that in mind for a second. And you'll see here different classes defined by astronomers of the 20th century. The dominant lines in the spectra, the color of those stars, the color index by a mathematical definition, and therefore the temperature. And if you see down here in the 6,000 range, that color of that star is yellow, which is even more intriguing, right? Because that corresponded to that one black body curve that was about 6,000 degrees, that had the peak right in the visible range. And now we know why, all right? Because without further ado, around 6,000 Kelvin, and it happens to be our sun. And here are some of the other stars. Betelgeuse, which is a red giant, is relatively cool, but look at its luminosity comparatively because it's huge. And then Sirius, which is very bright. Magnitude to us because it's very close to us, but really compared to Betelgeuse, not that bright at all. From a luminosity standpoint, not very bright at all, but its temperature is very warm. And here's Rigel, which is further away from us, but even hotter than Sirius. So if you take all those various color temperatures, those temperatures of stars, and you plot them versus the luminosity versus their spectral type, the amount of light they're giving off, you get this very famous diagram in astronomy, the Hertzsprung-Russell diagram, or the HR diagram. And these stars are all like our sun. They're on the main sequence, and they're burning hydrogen. These stars here are white dwarfs down here, and these stars here are red giants and supergiants. But this star, these are all the stars in its main portion of hydrogen-burning life. The sun, just for your knowledge, is a G2 778K star on this chart. I bid adieu. So all good things come to an end, and that includes stars. Red giants and supergiants. When the sun ends up using its hydrogen fuel, it will collapse, and its core will get hot enough and begin to fuse helium to carbon and oxygen. Okay, once that fusion of carbon and oxygen lights off, the new a new hydrostatic equilibrium is reached, except it's now big. It's a red supergiant. The more massive stars will repeat this process. And by the way, this isn't a supernova or a nova or anything. It's not quite that energetic, but you can bet that's a pretty energetic event when this happens, right? And so a lot of materials thrown off and all that cool stuff. Not cool for us, because we happen to be, if it happens to the sun and we happen to be around at the time. More massive stars will repeat this same process, but where it stops depends upon its mass. So hydrogen going to helium, then to carbon and oxygen, and then neon, and then various other elements. And all these elements will exist kind of simultaneously as concentric active cores found in massive stars. So it'll still be burning hydrogen a little bit on a bigger core, and in the inside will be eventually heavier and heavier elements. Successive fusion types will require hotter temperatures and give off more energy. The new equilibrium is reached, the hydrostatic equilibrium. The sun or star will expand to become a red giant or a red supergiant, depending upon what's going on inside. And then we'll keep going until it reaches, unfortunately, iron. Iron fusion doesn't happen. Iron's different from the other elements. Iron, instead of giving off material for the giving off energy for the amount of energy required to fuse it, it actually takes more energy than it gives off. So iron just stops the process. And when that happens, hydrostatic equilibrium is gone, and the sun or star will continue to collapse until something stops it. What besides fusion stops a star from collapsing? We already know fusion keeps it up, keeps the star, the gravity from taking over. What else will stop a star collapse? Electron degeneracy holds up white dwarfs. So our sun will turn into a white dwarf. Particles with like quantum values must stay, again, particle physics is weird. The particles with quantum values must stay separate. That's called the Pauli exclusion principle. The free electrons in a star order to themselves and provide a back pressure that resists gravity, and that is a white dwarf. If electron degeneracy isn't sufficient, in other words, if the star is big enough, the remainder of the star is big enough, at under 1.5, so a star that's about 1.5 solar masses or higher, the star will continue to collapse. Gravity is too much for even electron degeneracy to hold it up. Neutron degeneracy takes over, and that's where a neutron star comes in. Neutron stars actually act, because the physics of small particles are universal. So neutrons actually act the same as electrons. That same process is holding up the star, resisting the gravity. Those small particles have quantum values that must remain separate. However, neutrons are excluded, are a little bit different in this case because they get an additional assist. Neutrons are subject to the strong force, and the strong force is weird. The strong force holds particles together inside an atom, so there's an extremely strong pull. However, they don't allow particles to, the strong force doesn't allow the particles to get too close. So if they get too close, it actually starts pushing on the particle. So we're used to gravity, which has one direction, towards the center of mass. This particular force has two directions. And so neutron stars get an additional assist to the strong force, and they can support between 1.5 and about 3 solar masses. More a little bit if the star has spinning particularly fast. Beyond those opposing forces, I've got nothing. And guess what? Neither does the professional astronomers or the rest of the universe. The star remnant will continue to collapse, and what happens to it? Black hole. All right, so that's what happens when you get over this value here. Do not go gentle. So this here and this here are two different, we talked about them. This is actually, like I said, it's a pretty energetic event, even if it doesn't go nova or supernova. Here's a planetary nebula. And this is the Ring Nebula is a planetary nebula, and this is what happens when a star about the size of our sun dies and goes into a white dwarf, and it threw out its upper layers of the plasma in the sun. And what's happening, and why this is such a pretty object, is that the plasma is recombining. Those electrons and the protons are finding each other and forming back into helium. And the waves of the atmosphere being shed catch up to each other, and so when those electrons and protons recombine, energy is given off. That energy is light, so this is actually a luminous object. It actually gives off light when that plasma recombines. And so you can see planetary nebulas, the Ring Nebula being one of them, which we will not be able to see tonight, unfortunately, but is a nice object to see in the sky. This is the Crab Nebula, and this is actually a supernova remnant, and there is I believe it is in the Crab Nebula's case, a neutron star in the center of the, and so that went through the more violent process of creating a neutron star as opposed to the white dwarf that's in the center of the Ring Nebula. So that is my presentation, and we can talk about black holes and solar remnants. That's a whole separate subject and very interesting, but we won't go into that as much. But I do say to everyone to join an astronomy club up here, one of the local clubs, and I want also everyone to stay safe this evening. That's it. Thank you.
All right. Thank you, Paul, for a wonderful presentation. So at this time, we're going to have a question and answer session. And we have been live streaming this presentation so that, with COVID, if you ever can't make it, or, you can always catch our presentations online through our YouTube. Again, you can visit our website to get to it. So while I'm waiting for any last questions from our online audience, let me go over a couple things before we have that. So if you notice, it is kind of dark. When we go to leave, please use your headlights. It hurts to get run over, and we'd prefer not to have any more people find out. Don't ask. Yeah, it hurt, If you guys need to use the bathroom, you do have the porta potty to my right, your left. And also consider visiting our gift shop. All the proceeds go to keep us operating and help keep us offering free public programs and outreach events. Or at least we will have outreach events once the plague allows us to. So,
just one more thing here. We have our donation jug out. So we are a volunteer organization, everyone. So if you do have, the means, we would certainly appreciate any generosity. Thank you.
Right. So unfortunately, like Paul said, it is rather cloudy. Even the moon looks like a dust bunny I found under my dresser. So unfortunately, the telescopes aren't exactly going to be viewing anything tonight. However, I believe one of our co-volunteers does have a slideshow running over on one of the observatories, and we may have one of the doors at least open so you can see one of the scopes, at least. So, were there... There's like 3 or 4 going on. Oh, wow. I was wrong. There are 3 or 4. This is things they don't tell me before I come online. So, were there any questions from our live audience? Or are we just crickets? All right. So, since there doesn't appear to be any questions from our online audience or any questions from our live audience, I want to thank you all for joining us and have a good night.
Thank you, everyone.